There's a recording. So chemical equilibrium is something that we've really ignored when talking about chemical reactions because most chemical reactions don't just go all reactants to all products, and you end up with none of the reactants. Most of them will find some sort of balance, whether it's biased towards the reactants or it's biased towards the products. So we call this a dynamic equilibrium because in any chemical reaction, if it's going on in a flask, it never actually stops going in the forward direction or going in the reverse direction. So that reverse reaction is also happening. But at some point, those rates of the forward reaction and the reverse reaction end up being the same. So this is kind of like traffic on the freeway. If there's the same number of people driving north on 99 as are driving south on 99, that's sort of a dynamic equilibrium. Because if you checked at any point for a certain stretch of freeway and counted the cars, north of 1 point or south of 1 point, it would be the same. It would be constant. And you could keep checking, unless something changed the equilibrium. We could say, for example, like a car accident stops everything going north, then there would be no cars north of that point on the accident, or very few, and mostly cars on the opposite side. So this equilibrium, it's like an active process going at the same rate in both directions. So our chemical system is at equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. Right? So we're continuing to make products, but some of those products are returning to reactants. The rate of a chemical reaction, so how fast is that forward reaction going or how fast is the reverse reaction going, is a measure of how fast the reaction proceeds. So you think of rate, like when you're driving a car, it's the rate of speed. Thought I'd have another example there. Or if you're trying to make, tacos or something, right? It's how many tacos you can make per an amount of time. It's also the amount of reactant for chemical reactions, the amount of reactant that changes to product in a given period of time. So reaction rates can be controlled if we understand the factors that influence them. And I think we're going to talk about two things first, and then we'll talk about another one later. But they are really integral to everything about equilibrium and chemical reaction rates. So if you can grasp those concepts and see how they affect everything else, you can start from there and figure it out later. You don't have to memorize everything. So the thing that really underlies all of this is collision theory, that chemical reactions occur through collisions between molecules or atoms. So the molecules or atoms have to actually hit each other for a reaction to happen, otherwise they can't react. So with hydrogen and iodine, those hydrogen and iodine atoms have to, or molecules in this case, have to hit each other to react and become hydroiodic acid. The other thing with this is they have to hit each other, but they also have to have enough energy for the reaction to proceed and form products. If they don't collide hard enough, there won't be any reaction. And then collision energy, right? So how much energy does one of these collisions have? It's exactly the same if you were, driving a car and you hit something. It's related to particle velocity, right? So the faster you're driving your car, the more energy you're going to have if you hit something. It's the same thing with particles. If they're moving faster, they have more energy. And gas phase molecules, this is actually true of liquids as well, have a wide distribution of velocities or speeds. So you'll have some that are moving really slow, you'll have some that are moving really fast, but the number of, or proportion of ones moving fast or slow is going to be dependent on the temperature. So as you heat something up, you're going to have more particles with more energy. As you cool something down, you'll have more particles with less energy. And high energy collisions lead to products, while low energy collisions do not. So we'll introduce this idea of activation energy right now, but we'll come back to it. So activation energy is exactly how fast or how much energy the particles have to have when they collide to actually react, to activate the reaction. That activation energy is because usually there's bonds already in place, so you have to hit hard enough that those bonds break, and that new bonds can be formed with the products, or to form the products. So everything that we're going to talk about that influences the rate of reaction will be the same factors that affect the number of high energy collisions that occur per unit time. So if we get more collisions with more energy, we'll have faster reactions. So more collisions equals, well, let me write it this way. More collisions equals more reactions. More energy equals more reactions. And when I say reactions here, I mean two particles when they hit reacting with each other to form the product. So one of the things that we can do to increase the rate of a reaction, which is increasing the number of collisions, is to increase the concentration. So increasing the concentration, the reactants or the products really, means we'll have more collisions. If we have more things colliding, we'll have statistically more things that have the energy in those collisions to react. So higher concentration means more collisions, because higher concentration means more particles. Over the course of a reaction, the rate decreases as reactant concentrations fall. So every time one of those particles or two of those particles collide and react, it removes a possible reactant from colliding again. And so we have fewer and fewer collisions as we use all of those up. It's kind of like if you're eating Skittles and you only wanted to eat the green Skittles. As you eat more and more green Skittles, there are going to be fewer in the bag or whatever you're eating out of. So it's going to be harder and harder for you to find a green Skittle. So we're decreasing the rate that those reactions take place because there's fewer collisions. What is that? Okay. So the other thing we can do is we can increase the temperature. Because remember, we need enough energy to react. So increasing temperature, raising temperature, makes the molecules move faster. So not only does that give them more energy for collisions, because they're moving around faster, they're going to collide more often. So to summarize this all, 3 important points. Reaction rates generally increase with increasing concentration. So increasing concentration, increasing temperature, and then they decrease as the reaction proceeds because our concentration's dropping. And this is all collision theory. So just focusing on getting more particles interacting and getting them to interact with the most, or the energy needed to react. All right, so in a chemical reaction between two gases, you would expect that increasing the pressure of gases, would it increase the reaction rate, decrease the reaction rate, or not affect it at all? Yeah, but why? What happens as we increase the pressure?
Don't they move around a lot faster? With that, there's more collisions.
There's more collisions? Yeah, so I think there's a few things at play, and it kind of depends on a couple things. So if we have a cylinder here, and we have some particles inside, remember concentration, usually we talk about it in molarity, so that's moles per liter, can work for gases as well. Right, so how many particles per unit of space inside the cylinder? If we decrease the amount of space, that increases the pressure, because now we have more particles in a smaller space. And so the concentration effectively has risen. And usually when we decrease the volume and increase the pressure, temperature does go up too, unless it's controlled. But yeah, so reaction rate increases if we increase pressure. Because for gases specifically, pressure is directly related to the concentration of the gas. All right, so a reversible reaction can proceed in both the forward and reverse directions. It's reversible. Doesn't take much energy to cause the reverse reaction. So the condition in which the rate of forward reaction is coming back to dynamic equilibrium. The forward reaction equals the rate of the reverse reaction. That's our dynamic equilibrium. It's kind of like walking up the down escalator. If you're walking up the down escalator, you're walking up at the same speed that the escalator is going down. You don't move, right? If you want to get to the top, you have to walk faster than the escalator to get to the top, or if you walk slower, then you'll be taken back down. But here at dynamic equilibrium, it's like walking at the same speed up the escalator as it's going down. So the key here is that these reactions are still occurring, right? So they don't stop. We don't hit equilibrium and then everything freezes. They're just balancing each other out. So because the forward reaction and reverse reactions are at the same rate, the concentrations of reactants and products no longer changes. Because every new product that gets made just as quickly gets turned back into a reactant. So one of the ways we can tell when we've reached that dynamic equilibrium is that the concentrations don't change anymore. So if we look at snapshots of a reaction, at T0 we've got all hydrogen and all iodine. At T15, now we've used some of that hydrogen and iodine to make the hydroiodic acid. If we check the concentration again, let's say it's 30 minutes. Now we have, again, less hydrogen, less iodine, more hydroiodic acid. And then if we check it again at 45 minutes and we see that the reaction concentrations are the same for products and reactants, then we know we've reached equilibrium. So it's the easiest way, well, as long as it's easy to measure the concentrations, it's the easiest way to tell that you're at equilibrium. It doesn't necessarily mean that concentrations are equal. So the forward reaction, the reverse reaction might be affected by the concentration differently. They might be affected by temperature differently. And so that equilibrium just means the concentrations aren't changing. It doesn't mean that the concentrations are the same. This is in the book, believe it or not. I didn't come up with this one. So if you have the situation where Middle-earth from Lord of the Rings and Narnia from Lion, the Witch, and the Wardrobe, what is it, C.S. Lewis? I can't remember what the series is called. So if you've got these two magical lands next door to each other, and Narnia is full of people, and Middle-earth is empty, then the people at Narnia are going to say, hey, there's a bunch of land over there, there's nobody hanging out, let's go hang out over there, let's go live there, because we're going to have bigger houses or whatever, more space. So as people start to move over to Narnia, or move from Narnia into Middle-earth, then that draw gets less and less because it gets more and more crowded. And eventually some people will be like, well, now it's better over in Narnia than it is here, so they'll start moving back. And those rates eventually will become equal. Oh, this actually reminds me. There was another thing I wanted to mention. There's Crash Course Chemistry YouTube channel. The videos are old, but it's chemistry, so it's still very, very good stuff. But it's by Hank Green, if you know who he is, pretty famous on TikTok at the moment. He has a series that he does called Crash Course Chemistry, and the 10-minute chemical equilibrium video is really good, just talking about the concepts of equilibrium. So it's 10 minutes. I would recommend you go watch that. And there's a bunch of other ones. Okay. So at equilibrium rates, the forward and reverse reactions are equal, not the concentrations, as we just covered. So what can we then know about those concentrations? And it turns out, of course, if the concentrations don't change, then they exist in some proportion, right? We can count, there's literally count how many more products there are than reactants, or fewer, and we can use an equilibrium constant, which is a ratio between those equilibrium concentrations. It's equilibrium constant, and quantify exactly how much more product we'll have than reactant, or how much more reactant we'll have than product. So, got a generic chemical reaction here, right? Obviously not a real chemical reaction. A and B are reactants with coefficients of lowercase a, lowercase b. Capital C, capital D, those are our products, again with coefficients that are the lowercase c and d. So the equilibrium constant for the reaction is defined as the ratio at equilibrium of the concentrations of products raised to their stoichiometric coefficients divided by the concentrations raised to their stoichiometric coefficients. So that's what this guy is down here. Let me zoom this a bit. All right, so we've got our products on top. We've got capital C, which is the capital C here, raised to the lowercase c, multiplied by concentration of D, raised to coefficient of D, divided by A to the A times B to the B. So for any equilibrium expression, or for any chemical reaction, we can write an equilibrium expression. Oh, I remembered what I wanted to say. The brackets again, brackets mean molarity, which is moles per liter, right? So brackets mean the concentration of the thing in brackets. So for this chemical reaction, we can write this equilibrium expression where you have the products on top. And so it's the concentration of NO2 raised to the fourth power because it has a coefficient of 4 in the balanced chemical equation. And we multiply that by the concentration of oxygen raised to the first power. because anything raised to the first power is itself. We just kind of leave the 1 out because it's implied. And then for our reactants, it's just N2O5 raised to the second power because its coefficient is 2. So it's very, very formulaic. Of course, as with almost everything in chemistry, there's an exception to the things that you add to this, but we'll cover those. All right, so if we want to practice this, write an equilibrium expression for this chemical equation. You want to first check that it's balanced. So here, just double check, right? 2 hydrogens in the reactants, 2 hydrogens in the products. It's balanced. So this is going to be KEQ, equilibrium constant, equals. And then it's always products over reactants. So concentration of the products raised to the second power. Concentration of H2. Do we raise that one to a power? No. And then concentration of F2. And that is the equilibrium equation for this chemical reaction, or equilibrium expression. It might also be called an equilibrium expression. Cool. So what does this tell us then about any reaction? When KEQ is large, that means that the forward reaction is favored, meaning that the forward reaction is happening a lot faster than the reverse reaction, and that we'll have more products than reactants at equilibrium. So we have something like here, KEQ is 1.9 times 10 to the 19. That means that our concentration of products is going to be much, much, much greater than the concentration of our reactants, because we'll have a big number as the concentration of the products. And let me write this out real quick. So this would be the equilibrium expression for this. Right, so if we want KEQ to be this very large number, it means the number on top of our equation has to be a lot bigger than the number on the bottom, or the denominator. So the concentration of HBr will be a lot more than H2 or Br2 at equilibrium. And the opposite is true when we have a small KEQ. That means that the reverse reaction is favored, or that the reverse reaction happens a lot faster than the forward reaction. And so there will be more reactants than there will be products at equilibrium. When these KEQs are very big or very, very small numbers, you just have to pay attention to the exponent. Negative exponent means a small number. Positive exponent means a big number. And in this case, this is times 10 to the 31, negative 31. So it's a very, 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 very small number, right? A mole is 6.022 times 10 to the 23rd. So times 10 to the negative 31 is very small indeed. So if we have a large equilibrium constant, these are our models here. That means that there are a lot of Br2 molecules, and we've only got one of each H2 and Br2 molecule. A lot more products than reactants. For the small equilibrium constant, it's the opposite. We have most of these in the box are the reactants, and we only have a couple products that were formed. Okay, so summary of this is, if KEQ is really small, This less than is like really, really small, or really, really smaller than 1. The reverse reaction is favored. Reverse reaction is favored. So if the reverse reaction is favored, are we going to have more products or reactants? Yeah, reactants. If it's close to 1, then neither direction is favored, and the forward reaction will proceed about halfway. And you'll still have significant amounts of both reactants and products at equilibrium. When KEQ is a lot bigger than 1, the products are favored, or the forward reaction is favored, meaning we have mostly products. So here's the exception. If we have a reaction that includes solids or liquids, those are left out of the equilibrium expression because they're constant. If you think about water, pure water has a molarity of 55.5 moles per liter. Most of the stuff that we work with is like 6 moles, usually even smaller than that, like 1 mole. So the concentration of the water is so high that it's essentially infinite, and it doesn't have any effect on the equilibrium expression. Same with solids, because only the stuff that's actually dissolved is going to be part of the reaction, and as that reacts, then more solid is added. And so we leave them out. So for an expression like this, remember the S in parentheses means solid. So calcium carbonate, calcium oxide, both solids. Carbon dioxide, though, is a gas. So the only thing that actually is part of this equilibrium expression is the concentration of carbon dioxide. Okay. So we want to write the equilibrium expression for this equation. KEQ equals, and what will our products be? Oh, wait.
H2O squared.
I messed up a little bit. So H2O is liquid. So I shouldn't have written 2 sets of brackets. But H2O is a liquid, so we leave out liquids and solids. So we're going to,
Cl2 squared.
yeah, it'll just be Cl2, and then, yeah, squared, because it has the 2 coefficient. And then for our reactants, what do we have?
HCl and then to the 4th power.
Mm-hmm.
And O2. You don't put anything on top.
Yeah, technically to the first, but we can leave it out, it's implied. Yeah, so just always make sure you're checking for those solids and liquids.
So those solids and liquids you never add.
Never part of the equilibrium expression. Yeah. Excellent. Are there any questions on any of this so far? Cool. Don't worry, it'll get more confusing. Doesn't get that. No, equilibrium's not so bad. So, I don't know if you noticed, but earlier when we had some equilibrium expressions, temperature was a part of that, right? Because temperature affects the rate of reaction, but it can affect the rate of the forward reaction and the reverse reaction differently. So high temperatures might increase the rate of the forward reaction more than the reverse, and so it'll shift your KEQ. So it's specified. It's like, okay, so this is the equilibrium expression at 25 degrees C, but it doesn't really play any role in the actual calculations. We use concentrations in moles per liter, but we drop those because we're using the brackets to show that we have concentrations. The concentrations, actually there's a nice table for this. The concentrations will not always be the same at equilibrium, right? So it won't always be 2 moles of product and 1 mole of reactants, but it'll always be the same equilibrium constant. So let's say for one of our reactions we get 2 moles of product let's just say it's 2 over 1. We'll make it really easy. You don't necessarily need to have those concentrations to get that same ratio. So, right, this is product, reactant. We can get the same ratio of 2 to 1 with 4 to 1. Or sorry, not 4 to 1, 4 to 2. Product to reactant, or 3 to 1.5. But when you divide 2 by 1, you get 2. When you divide 4 by 2, you get 2. You divide 3 by 1.5, you still get 2. So the ratio between them is always the same. They might be different numbers for the actual concentrations. All right, so let's throw some numbers at one of these. Because our equilibrium expression lets us calculate the equilibrium constant. So we'll suppose somebody did this reaction. They had a mixture of hydrogen and iodine reacting to become hydroiodic acid. They did the reaction at 445 degrees Celsius. And we're given equilibrium concentrations. And we're asked to find the equilibrium value. So the first thing we do is write the equilibrium expression for this equation. So we'll check to see if there are any solids or liquids. Gas, gas, gas. So we don't have to worry about that. And then this will be the concentration of our product squared divided by the concentration of H2, the concentration of I2. And then the thing that always used to mess me up on these problems is I would take the wrong concentration, or I'd take the concentrations and plug them into the wrong spots and get them swapped as I was plugging numbers in. So be vigilant there. But that's all we have to do now. We just plug these numbers in and then a little bit of math to calculate the equilibrium constant. So 0.78 squared over 0.11 times 0.11. So 0.78 squared divided by 0.11 divided by 0.11. So our equilibrium constant is going to be, with 2 sig figs here, which is kind of annoying. 2 sig figs would have to be 5.0 times 10 to the 2. And then that's at 445 degrees C. So you just plug some numbers in. Make sure you do everything in the right order of operations. So this was the table that I was talking about that shows this, where we don't need to have the same concentrations to get the same equilibrium constant. So this is for the reaction we were just looking at. So here at equilibrium, that's 0.11, 0.11, and 0.78. So that gives us an equilibrium constant of 50. But if we instead had started, so they started this reaction with 0.5 molar hydrogen and iodine. But if we start with none of the hydrogen and iodine and instead start with 0.5 molar hydroiodic acid, let this reaction sit for a while, come to equilibrium, we would get 0.55 molar hydrogen and iodine because some of that reverse reaction would happen. And we'd be left with 0.39 molar hydroiodic acid. If you plug all those numbers in, you'll get still an equilibrium constant of 50. So no matter how you set these up, right, 0.5 molar of all of these, or 1 molar of this and 0.5 of that, these numbers will all always come back to 50 when you plug them into the equilibrium expression. Equilibrium constant expression. All right, so we got another one here. So what's our first step for a problem like this?
See if it's balanced.
See if it's balanced. That's good. It's not what I was thinking, but that's good. Yes, it does look like it's balanced.
See if there's any liquids or solids. Yeah, solids.
Solids or liquids, yes. Because, yeah, we're going to leave those out of the KEQ. So then it's just products over reactants raised to the exponent of their coefficients. So that's methanol, coefficient of 1, carbon monoxide, coefficient of 1, hydrogen, coefficient of 2. And then we can plug these numbers in, being careful to stick them in the right spots and not leave out any exponents. Cool. So 0.151 divided by 0.489 divided by 0.146 squared. So with 3 sig figs this time, 14.5 will be our equilibrium constant for this equation, and that's at 225 degrees C. Okay, so we can also use this if we have, all the other pieces of data. If we know what KEQ is, we know the concentration of 2 of our species from a reaction, we can use those to figure out what that third species, or 4th species, the last species concentration is at equilibrium. So for this reaction again, we want to check if it's balanced. We want to check for any solids or liquids. Show how many solids or liquids, just gas. But we'll start this the same way, in that we'll write our KEQ expression. So this is going to be carbon dioxide, carbon tetrafluoride over, I should know what this one's called. Carbonyl fluoride? No. Fluoroformaldehyde? Okay, so then we can plug in the numbers that we do have. So we have KEQ, which is 2. So 2.00. We don't have CO2 actually, so that's what we're going to be looking for. But we do have CF4, or carbon tetrafluoride. And we have COF2, 0.255 squared. So you could do this in a number of different steps. I'm going to, what am I going to do here? I'm going to do 0.118 divided by 0.255 squared. And then I'm going to take 2 and divide by 2 and divide by the answer that I got from that previous calculation. So this will be 1.10 molar equals the concentration of CO2. You could have done 2 2 times 0.255 squared, then divided by 0.118. Could have divided both sides by 0.118 and then multiplied by 0.255 squared. Gotta love algebra. Okay. So we could have done that, right? If any one of those was missing, we could have solved for them if we have the other ones. So say for this expression here, again, you want to check that it's balanced. You're going to check that there are no liquids or gases, or look for those liquids and solids. But we just have iodine and monoatomic iodine, and we have a KEQ. So we're asked to find the we're given the concentration of iodine, and we're asked for the concentration of I. So what would the next step be? Fundamentally, it's the same problem that we just did.
So you're trying to solve for I, correct?
Mm-hmm.
Okay. So wasn't you like set it up in an equation?
Mm-hmm. Which equation?
Constant equilibrium.
Yeah, so we want to set up the equilibrium constant equation or expression. Expression and equation mean the same thing. So that's going to be concentration of I squared over the concentration of I2. So we can plug in 0.011 for KEQ, and we can plug in 0.10, and then this stays I squared. So we do 0.011, and we'll multiply that by 0.1. So we'll get 0.0011 equals I squared. So what's the inverse function of squaring something?
Square root. Yeah.
Square root. So we can take the square root of both of these. So this will be is that right? 0.25. Oh wait, 266. So I have 0.256. So just 26 would be 0.26, or equals concentration of I. Oh no. I did do that wrong. That didn't seem right. Hit the wrong button. Yeah, 0.033. That makes more sense. Yeah. It's possible to get situations, right? If this had been something with a 3 for its coefficient or 4, then you could get I raised to the 4. So the inverse of that is just the 4th root. On your calculator, the way you can do it. So for this one, we could do I squared, and most calculators have a square root button. Some calculators even have a button that looks like this, where it'll be the square root, and then it'll be like a box here. That button's nice because that box means, well, you could put a 2 in there and it's the square root. You could put a 3 in there and it's the 3rd root. 4 is the 4th, 5th, 6th, so on and so forth. If your calculator doesn't have that, the other thing you can do is if you want to do the inverse function of I squared, then you can take this thing and raise it to the 1/2 power. So if it was I to the third, then you just use I to the 1/3, or 1/4, or 1/5. All right. So if we have a chemical reaction, it's at equilibrium, what happens if we push it, if we disturb that equilibrium? Le Chatelier's principle is this concept. What happens when we push the equilibrium, when we disturb it? So when you disturb a chemical equilibrium, the system shifts and in a direction that minimizes the disturbance. So a system at equilibrium fights back when disturbed. So if you add more to a reaction, it's going to do whatever it can to reduce that amount that you added. We'll see what that looks like here in a second. Okay, so let's go back to Middle-earth and Narnia again. So let's say that they've sort of come to this equilibrium. There's constantly people moving back and forth from Middle-earth to Narnia and back, but the equilibrium has stabilized. Roughly the same number of people in Middle-earth, roughly the same number of people in Narnia. What happens if you add a ton of extra people to Middle-earth? Well, they moved there for the wide open spaces, and now there's a bunch more people who have just moved in, kind of like actually all of the people who moved from like LA and the coast to here, and well, not here in Reedley, but mostly Fresno and Visalia, because houses are cheaper and they could work remotely. Well, this is going to cause a lot of people to move out because they say, oh man, it's really crowded here now. I don't want to be here anymore. We're going to go find somewhere with more space, so people move to Narnia. So this is the way that the system, this is the way that chemical reactions work, in that if you add more to one side, it will shift the equilibrium so that there are more on the other side. So it'll take those products, if you add products, and make more reactants. So if you removed people from Middle-earth, suddenly there's a bunch of extra space, a bunch of empty houses. People will move from Narnia back to Middle-earth. So if we have a chemical reaction and we add more product to it, going back to this collision theory of chemical reactions, if we add product, the rate of the reverse reaction increases, because now we have more product that can react and become reactants again. So if you add product, the reaction shifts left to make more reactants, reducing the concentration of the products. I don't really like this diagram, but just very quickly, this is the N2O4, and NO2 is our product. So if we dump more NO2 in here, some of that will react and form more of the reactants again. So then the opposite happens if you add more reactant. If we increase the concentration of the reactants, left side of the equation, then the forward reaction increases because there's more particles, more collisions, faster reaction rate. And so the reaction shifts to the right to reduce that concentration. So if you increase the concentration, the reaction will work to decrease that concentration. And again, skip that. So if a chemical system is at equilibrium, increasing the reactants causes the reaction to shift to the products. Increasing the concentration of the products causes the reaction to shift in the direction of the reactants. Also, if you decrease the concentration of the reactants, it will sort of, I always think of it in my mind as kind of like two piles of sand, but I guess in a trough. So if you dump a bunch of sand on one pile, it's going to flow back over to the other side. If you take a bunch of sand out, then sand will come and flow back into that hole to help fill it up. We're doing good. We're doing good. Okay. So for this reaction, what is the effect of adding more Br2 to the reaction mixture? Are we adding product or reactant? Product, right? Br2 is, it's on the right side of the reaction, so those are the products. So if we add more product, which way does the reaction shift? To the left. Everything you own in a box to the left. What is the effect of adding more BrNO?
That's the reactant.
It's a reactant,
Right.
so it'll shift to the right. Right? It's just, right, if we increase this, it'll shift away from that. If we increase this, it'll shift away from that. But what if we removed some Br2? So if adding it pushes it to the other side, taking it out, shift it to the right. And when we're talking about the shifting, it's how the concentrations change after you add something to it. So if we increase the concentration of Br2, then the reverse reaction speeds up, and we form more BrNO. So the reactants and concentration goes up, that Br2 concentration will go down, and to react and go in the reverse direction, the concentration of NO will also go down. Oh, I can write these in. So this will go right. Sorry, this will go left, right, and right. Righto. All right, this is the part where it does get a little confusing. But again, remember back, we talked about this a little bit with that one question. Increasing the pressure for gases is like increasing the concentration. So if we have, again, a piston, right, there's no way out. There's no way for any of the gas to get out. If we take that piston and we shrink it, then we are decreasing the volume into a smaller space, right? Think bike pump. You're decreasing that volume, that increases the pressure. So it means that those particles that are in there are now in a smaller volume, which is a higher concentration. So decreasing volume increases pressure. If we increase the volume, we decrease the pressure. So lowering the number of moles of a gas results in a lower pressure at constant temperature and volume. But a system can relieve pressure by changing the moles of gas. And we'll see what this looks like. So for a reaction, so again, decrease in volume increases the pressure. In order to bring the pressure down, the equilibrium will shift to the side that has less gas particles. So zooming in on this. So if we've got this chemical reaction, right? So this is 1 nitrogen, 3 hydrogens to make 2 ammonias. All you have to do is count the moles of gas on either side. Right? So all of these are gases. We have 4 moles of gas on the reactant side of the equation. We have 2 moles of gas on the product side. So if the pressure increases, the system will shift right because there will be fewer moles of gas inside of the cylinder. So you're sort of condensing them down. You can think of it almost like Russian nesting dolls, right? If you want those dolls to take up less space, you don't leave them all unpacked, not inside, nested inside of each other. If you need to conserve space, you'll take those and you'll stack them inside of each other. so they take up less space. And that's kind of what's happening here, right? You don't put the bowls into the cabinet like so they take up the maximum amount of space like this and like that. You can flip them and they will sit inside of each other so they take up less space. So if we increase the pressure, then it'll shift to the side with fewer moles of gas to take up less space. Of course, then the opposite is true for the exact same reason. If we increase the volume, then the pressure decreases. To counteract that change, the reaction will shift to the side with more moles of gas because it wants to stay at the same pressure. It'll try to maintain that equilibrium. So if you increase the volume, decrease the pressure, then the reaction will move towards the side that's going to increase the pressure again. This is actually a famous reaction made by Fritz Haber, who was arguably a terrible, terrible person because his original goal was to try and make nitrogen compounds which make explosives, and I believe he might have been a literal Nazi. He was alive in World War II, I believe. He inadvertently, though, came up with this reaction that creates ammonia, which is used in fertilizers. And so while his bombs killed hundreds of thousands of people, his fertilizer making process saved probably millions and millions and millions of people. It's a weird dude. Okay. So decreasing the volume will cause the reactor to shift in the direction that has fewer moles. Increasing the volume causes the reaction to shift in the direction that has more moles. And then if the moles of gas particles on both sides is equal, then it won't change. So if you have the same number of gas particles in the products and reactants, changing pressure has no effect because it does nothing to the equilibrium, assuming temperature stays the same. All right, so if we've got this reaction at equilibrium, and we've got all gases here, so SO2 gas, oxygen, and SO3 gas, what is the effect of decreasing the volume of the reaction mixture?
So it increases the pressure, right?
Mm-hmm.
And it's decreasing.
Yep, decreasing volume increases pressure.
So are you trying to ask,
Which direction
does it shift?
does it shift, if any?
So wouldn't it shift away? So I'm guessing go up.
If we,
Well,
it depends.
Yeah.
Depends.
Away, so that has less moles of gas particles,
Uh-huh.
right?
Yep. So which side is that?
To the right.
To the right. This is 2 and 1, so this side has 3 moles of gas particles. This side only has 2 moles. So volume, let me do it like this. Volume goes down, pressure goes up. So reaction shifts right. So what if we increase the volume of the reaction mixture? So volume goes up. What happens to pressure?
Down.
Goes down.
Increases pressure.
Pressure goes down. So how could the reaction shift to counteract the decrease in pressure?
Fill.
The reaction shifts left. So I think the hardest thing to keep straight is how the volume affects the pressure, and then realizing the number of moles of gas on each side. And then if the number of moles of gas had been the same, the answer to both of these would have been no change. Yeah.
So, like you're saying, the amount of moles of gas, like 2SO2, and then obviously it's 1O2,
Mhm.
right? So do you just like add them up on the side, like on, like for example, the reactant side, and
Mhm.
then just see like, okay, which one's bigger? If not, then you go to the right. If not, go to the left.
Yeah.
If that makes sense. Okay.
Mm-hmm. Yeah, you just count for the reactant side how many moles of gas there are. Count for the product side how many moles of gas there are. Then you say, okay, volume decreased. That means pressure went up. That means we want to go to the smaller number of moles. And I think that like one thing goes up, one thing goes down. I go left, you go right. That's where the confusion happens. So this could be a good candidate for. I don't remember. There's like one or two of these on the practice final, but. Might earn some space on your cheat sheet. All right, so we'll summarize very briefly all the things that we've covered. So we've talked about equilibrium. We've got equilibrium expressions, and then we can shift equilibrium by either adding or removing products or reactants. Right, if you add something, the reaction shifts away. If you take something out, the reaction will shift towards where you took the thing out. Then we talked about volume and pressure, just covered, right? So if the volume goes down, pressure goes up, then we shift to the side with the smaller number of moles to decrease the pressure. Now we can talk about the change of, or the effect of temperature on equilibrium. So, and particularly here with endothermic or exothermic reactions. So for exothermic reactions, heat is a product, or we can think of heat as a product. So if we raise the temperature of an exothermic reaction, and let me just, A plus B, C plus heat. So right, heat is one of our, or we're thinking of heat as one of our products. So if we add heat to the product side, or if we add heat, it's like increasing the concentration of a product. So which way would the reaction shift? I'll erase this. Somebody new. Left. Yeah, it just shifts to the left. So we're adding a product, reaction shifts to the left. For an endothermic reaction, we think of heat as one of the reactants, meaning it's on the left side. And so if we add heat, if we heat up this whole reaction, we're adding to the reactants, which will push us to the right and give us more products. Yeah, so endothermic reactant, exothermic product. And I think, at least in terms of trying to like keep these straight, where does the heat go? If you think of an exothermic reaction, that's like burning something. That produces heat, right? Produces product. And then you know the endothermic will have heat as a reactant. So Haber-Bosch process. Nitrogen plus hydrogen giving us ammonia also produces heat. So if we add heat to this, then reaction will shift to the left. If we remove heat, then we can actually shift the reaction to the right and get more product out of it. In endothermic reactions, now heat is one of our reactants. So this is a cool reaction, actually, and there's a picture of it on the next, I think it's on the next slide. If we add heat to this reaction, we'll shift this over to the products, endothermic reaction. If we remove heat, then it'll shift to the left, because we're, in essence, removing one of the reactants. So, wish we could actually do this one, but this is a sealed glass ampule in, I don't know, a cup or something. On the left, we have, it's been warmed up. So if heat's one of the reactants, then that shifts it over to the product, which is that brown. And then if we cool it down, then this reaction will shift over to the left, or reactants, and we'll have the colorless dinitrogen tetraoxide. So for exothermic reactions, heat is a product, and then all of the rules that we talked about in terms of increasing concentration of products, decreasing concentration of products, apply to heat the same way. In an endothermic reaction, heat is a reactant, and again, same rules apply. Okay, so the following reaction is exothermic. So where can we think of heat as being as a part of this reaction?
On the right side.
Yep, it's one of our products. Producing heat. So what is the effect of increasing temperature on this reaction? If we increase temperature. My fly's been down the whole time. Increasing temperature. Which way will it shift? To the left. So increasing temperature means we're adding more heat. So the reaction will shift left. And then if we decrease the temperature, to the right. Nice. It's not too confusing. The hardest part is, well, pressure and volume I always found to be the most confusing. For this, just got to remember which side heat goes on. That's left or right. This is excellent. We're getting close to finishing these. So the process by which an ionic compound, so that's metal plus a nonmetal, the process by which an ionic compound dissolves is an equilibrium process. So how much of that actually dissolves is dependent on the equilibrium expression for it. We call this a special case of the equilibrium expression, the solubility product constant. So it's the equilibrium for the chemical equation that represents dissolving an ionic compound. Remember, solids are emitted from the equilibrium expression. But in a similar way to our other reactions, a large KSP means that the compound is very soluble, because if I just use, let's say, calcium oxide dissolving in water, then this is calcium 2 plus O2 minus. So if this is dissolving in water, we're producing these ions. So our product here, in this sense, is the ions from that soluble, or from that solid. So large KSP means lots of products, means very soluble. Small KSP means not very much product, also not very soluble. Right? Most of it stays in the solid form. So the reason that this is a special case, because we use the same rules for writing out the equilibrium expression, we just leave out the solid, and it's for a somewhat simplified chemical reaction. So it's just barium, right? So barium doesn't have any coefficient, times the concentration of sulfate. Again, no coefficient, no exponent. And then what we're leaving out here is the reactant, which would be the solid barium sulfate. So we write these out almost exactly the same. But we do write them out the same. So even for these compounds that aren't very soluble, most of these are pretty much insoluble, there's still a small amount that dissolves, which is what this KSP tells us. Some of them, where is it? Oh yeah, this one. Copper sulfide, that's 1.27 times 10 to the negative 36, means that almost none of this is going to be dissolved. The most soluble thing on here would be calcium sulfate, which is 7.1 times 10 to the negative 5. So still not very soluble. Okay, so if we're going to write an equilibrium expression for an ionic compound, the first thing we need to do is write out that equilibrium reaction equation. And that is just going to be AgI, or silver iodide, which is the solid, and then the ions that it would produce. So in this case, it's going to be Ag plus, that's aqueous, plus I minus, which is aqueous. So what's KSP going to look like?
So it does not include solids, right?
Does not include solids.
Ag plus I minus.
Mm-hmm. And then we'll put these in brackets. Ag plus times, I mean, you can put the dot or multiplication in there if you want, really, but times molar concentration of I minus. Yeah.
So how do you, I forgot, so to like determine whether it's aqueous or not, or like if it's a solid, just look at your periodic table?
No.
You have to do like a form, or is it like a
There's-
table, right?
No. Here, there's some implied going on here in that this is asking for KSP, which is going to be the solubility product. So we know that this is a solid.
Got it.
And then the amount that it's soluble would be these ions. Unless you know it's a solid or a gas or a liquid, it's a pretty safe bet to assume that it's aqueous in at least this class and probably Chem 1 if you take Chem 1 or 1A.
Would we have to know, like, if it's aqueous or not for like the final, or do you worry about it?
No. I mean, you could just assume that these are aqueous for this. Okay, so for calcium hydroxide, what would be the first step? Go ahead.
Write out the formula, right? I don't know how to say it. KSP, yeah.
We could do that. We could start with there. Yeah, I mean, it's KSP.
Okay.
Now what? What are our ions? Huh?
OH? No?
OH will be one of them. Does it have a... Are we missing anything?
Yes, because OH is 2, right?
There are two OHs. So I think actually you could do it like this, just make sure that you see that there's a 2 here. Because the equation would be Ca, or the chemical the reaction equation would look like this. Ca2 plus 2 OH minus. So you can write this out. If you can do this part in your head to know that there's going to be 2 of those, that also works. Yeah, so there's your KSP. So the solubility of a compound is the amount that dissolves. We talked about solubility. The molar solubility is the number of moles of a compound that will dissolve in 1 liter of solvent. Right? It's just molarity, but it's how many moles dissolve per liter. We can calculate this from KSP, and we abbreviate it as S. And there's really just one trick to this. Sorry, I'll leave that there for a second longer. So the one trick is this. I sound like an internet ad. One weird trick. Chemists hate him. We write out the KSP equation. So that's, and here we're given the dissolution reaction. So KSP, KSP equals Ag plus times Cl minus. Then we can put in KSP that we were given. I'm doing this probably in more steps than it really needs to be done, but that's okay. And then the trick is this, that these ions are both produced from AgCl. And so what we do is, to figure out the molar solubility, which is, again, S, we substitute in S for Ag plus and Cl minus. So this becomes S times S. And I'll put this in here too, 1.77 times 10 to the minus 10. So this could be, right, S squared. And then if you had any exponents, which we don't here, if you had any exponents here, right, those would get added together when you multiply two things with exponents. So now we just take the square root of both sides. Oops. 1.77. And this is another one of those problems, one of those calculations where it's easy to type in just one thing wrong. So if you don't get it, if you don't get the answer that I get here, let me know and we'll figure out what you need to do on your calculator. So it's going to be 1.33 times 10 to the negative 5. That's the molar solubility of silver chloride. Actually, I think I could just put molar. So you would dissolve 1.33 times 10 to the negative 5 moles of silver chloride per 1 liter of water, which is not very much at all. I do realize too that it's 6:23, so if you've got to go, that's fine. We're going to finish this because there's only a few slides left. Let me see what's... Oh, yeah. These last slides will go fast, too, because we're going to do one more of these, and then we'll talk about catalysts. So calculating molar solubility from KSP. Again, you have calcium sulfate. What are we missing here? What do we need to solve this that's missing? KSP. So I'll have to go back and find KSP for copper sulfate, which is 7.1 times 10 to the negative 5. I would give you that on an exam. Okay. So you can, if you want, write out the reaction of what this would look like dissolving. So it's going to be Ca2 plus SO4 2 minus. and then we'll write out KSP equation, calcium 2 plus, and remember these are multiplied, so 4, 2 minus. And then we could skip some of the steps that I showed before, but I'm going to replace both of these with S, and then when those are multiplied together, we'll get S squared equals 7.10 times 10 to the negative 5. So 7.10 e to the negative 5, we want the square root of that. That's 0.00843 equals S. Because technically this should be molar. Or 8.43 times 10 to the negative 3. If you like scientific notation. And again, make sure you know how to take the square root or third root of numbers on your calculator. Cool. Any questions about KSP? Right. So, quickly with catalysts, which is funny because catalysts speed things up. So our equilibrium constant describes how far a chemical reaction will go. So how much products will have relative to how many reactants. The reaction rate describes how fast it will get there. But the activation energy for a reaction is the energy barrier required or that must be overcome in order for reactants to be converted into products. So we talked about this at the beginning. We do a few things. We could heat up the reaction, and that will give us more energy to overcome that activation energy. But there are a lot of things that are sensitive to heat. So if you're working in a lab, you need to do a reaction, you might not want to heat it up because it'll destroy your reactants or it'll destroy your product once it's made. So this is a reaction diagram. So reaction pathway, meaning that over here we have reactants, at the other end we have products. And we have the energy of those reactants or products. So the energy of the reactants has to climb up over this energy or activation energy hill in order to get to the other side where it becomes the products. The higher the activation energy, slower the reaction rate, right? Because you're going to have fewer actual reactants that are going to have that high energy required to get over the activation energy. And so the reaction will be slower. So if we want to speed things up, I guess the other thing we could do is add more or increase the concentration of the reactants. But sometimes reactants are expensive. We don't have very many to work with. Increasing the temperature, but again, some things are sensitive to heat. But we could also use a catalyst, which lowers the activation energy barrier, which is actually what people, when they steal mufflers, is what they're going for. There's a platinum catalyst inside, and that platinum catalyst is worth a lot of money. That catalyst is speeding up the reaction of, it's neutralizing sort of the waste products that come out of your car. So what a catalyst does, though, is it says, all right, instead of increasing the temperature, increasing the heat, increasing the concentration to like push over this hill, it says skip the hill altogether. And you can either go around the hill, or I kind of like to think of it as a tunnel going straight through the hill, right? So we're taking a shortcut that requires less energy than going over the hill. So it's providing an alternative pathway, right? So this is the original activation energy up here. With a catalyst, we can make that energy of activation a lot lower. Again, many things are thermally sensitive, so increasing the temperature would destroy them. So catalysts are necessary. And for living life, that's an oxymoron. Not an oxymoron, redundant. All of the reactions that keep us alive, that keep every living thing alive, would be too slow without catalysts. And so biological catalysts, called enzymes, increase those reaction rates. And they kind of do so in a cool, or some of them work in really cool ways. So the enzyme sucrase is a catalyst, creates a pathway with lower energy for the conversion of sucrose into glucose and fructose, because every sucrose molecule is made up of a fructose and a glucose linked together. Decreases the energy, breaks it down much faster. The way it does that is actually by grabbing onto the glucose and grabbing onto the fructose, and then holding them in a way that strains the bond between those two molecules, and allows it to be broken more easily. A lot of enzymes work like this. All right, there we go. Chapter 15.